Okay, let's get started. Today I want to talk about comparative effectiveness study, in other words, analysis of observational studies or non-randomized studies. We're going to basically talk about two different study designs, randomized and non-randomized studies. And then the issue with non-randomized studies is selection bias, and we're going to look at methods to at least make some attempt to overcome selection bias by the use of propensity scores, either matching or what's known as inverse probability weighting. So in a randomized trial, basically what happens is that randomization essentially equalizes potential confounders in the treatment groups. And so this is really the best method for establishing causality or for determining the effect of the treatment or whatever it is that you are particularly looking at. However, randomized trials are very expensive. And then there's an argument that you have limited data. In other words, it's data that people have volunteered to participate in, and then they've been randomly assigned to a treatment group. So the argument is that it may not reflect real-world practice. On the other hand, observational studies have the advantage that the data already might exist, like in an electronic medical record. And often in observational studies, you have registries where there's a lot of patient information. But the problem is when you go to analyze or compare treatment groups or different therapies, you have the potential for selection bias and confounding. So one way to do this is to match people in one group with the patients in the other group by different covariates, age, race, and sex being the primary ones, but there could be a host of others, whether or not they have diabetes, hypertension, et cetera. However, if you do this, then you're probably going to be limited to a few covariates. Because the problem is that the more covariates you include, like age, race, sex, and so on, you have too many categories. That is, you may not actually be able to you may not end up with enough patients in one particular categories. Say if you have the race, sex, diabetes, just those three alone, or including age, you might not be able to do that because of the small counts in a particular category. And then, so for example, if you have age, then how close are you going to match within a year, within 2 years, 5 years, 10 years? And so the smaller the match that you want to make, then the more difficult it is to actually match. Then another way that this is done, rather than try and match on different covariate categories, is to just include the covariates in a regression equation. However, the limitation here is that the number of variables are limited depending on how big of a sample. And so, as you may or may not know, sort of a rule of thumb is that you need at least 10 patients for every covariate or every variable you have in your regression. So this sometimes can limit the number of variables. So one way, or a more, I guess I should say, a better way of reducing selection bias is to do what we call propensity score analysis. And there's two different ways we can do this. We can do propensity score matching, or we can do inverse probability weighting. The latter having, at least in my opinion, more advantages than matching. So what we mean by propensity score is the propensity to be in one treatment group or another, where group assignment could be randomized. But in certain situations, you can't do a randomized trial because just of the nature of the treatments. What you can't use propensity score for is assigning comorbidity or risk to to a risk factor like diabetes. You can't assign a group to diabetes or no diabetes. A patient has no diabetes or has diabetes. It's that's a patient characteristic. So it's not something that you can create a propensity score for and then try to match patients on that. And so the way that we're going to do this is we're going to do a logistic regression where treatment group is the outcome. And we'll just use the example here of two groups. We can have more than two groups, but that becomes a little more complicated. We're going to match them on different demographic, clinical, laboratory values, and we're going to use as many as available. What you can't use in the logistic regression equation is the outcome. For example, if it's survival or lower blood pressure or whatever it might be, that cannot be a variable that's included in the logistic regression to generate propensity scores. And so what we're going to come up with is what's known as a quasi-randomized study. In other words, we're going to create essentially a randomized study, although it's not truly randomized in the usual sense of the word. So to create our propensity score, we're going to solve a logistic regression for each patient, where the probability of being in group A, we'll use that as the group that's of interest. And so our regression equation is just simply the logit of the probability divided by 1 minus the probability. And that's the regression equation where you have, in this case, the bold X stands for a number or an array of covariates. And so we would come up with a probability of A being the probability of being in group A. And then if the probability of being in group A is P sub A, then the probability of being in group B is just 1 minus that. And so when we create our propensity scores, then we're going to match a patient in group A and a patient in group B with the same propensity score. Of course, as you would anticipate, propensity scores aren't going to be exactly equal. So how close do we want the propensity scores to be in order to call the pair a match? And so one method of doing this is what's called greedy matching. So we set a criteria for a match. And so as an example, I've got examples here of propensity scores and how close they match in groups A and groups B. And so the first one there, the 0.245, they match out to 8 decimal places. The second one is an example where they match to 7 decimal places. The third one to 6, and so on. And so the criteria that you have to set beforehand is then how close of a match do you want? Are you going to allow? In other words, is say 60 versus 0.61, is that close enough for a match? And the thing about propensity score matching is that it turns out in your sample that not everyone is going to be able to be matched. And it turns out that about 30%, more or less, end up being unmatched, and then because they're not matched, they have to be excluded from the analysis. The other method is what's called inverse probability weighted estimation, where the probability is the propensity score. And so we get the probability in group A, as I mentioned before. The probability of group B is 1 minus that. And so we have n number of patients. We have the treatment indicator, whether they're in treatment A or B, which is usually coded as a 0 or 1. And then we have the response variable, whether it's survival or some measure of treatment benefit. So in that case, then we calculate the inverse probability of that by just taking the inverse of the probability score. And actually, it turns out most statistical software like SAS and Stata just requires a propensity score. They calculate the inverse of that then. And so what happens then is that because everyone has a propensity score or an inverse propensity score, then we can use all patients in the data set. And so the propensity score becomes the covariate that serves as the matching, but we can use all patients. And so then we can then also analyze censored response data using this method. The disadvantage, though, is in terms of the calculation of the propensity score and then its inverse, is if you have an unmeasured confounder. However, that's also a problem with matching. If there's some variable covariate that you haven't measured that affects the outcome, then you really are not sure whether your analysis is going to be correct as far as determining whether one treatment or one therapy is better than the other. So I want to do a couple of examples here, one where we do matching and then another one where we do inverse probability weighting. And so this comes from a study that we did some time ago on neonatal outcomes before the intervention and outcomes after the intervention. So obviously this is not something that you can randomize. The patients, the women before the intervention occurs are not likely to be included after the intervention. So this is sort of a schematic here of the study and the intervention. So we have women giving birth before intervention. The intervention occurs the following year, and then we have women giving birth after the intervention. So it turns out that the number of women after the intervention is about 4,700. So about 40% participated, or of the patients in 2006, about 40% actually participated in the intervention. And so here's a list of variables that we included in the logistic regression as either pre-intervention or post-intervention that we wanted to include in our regression equation to determine whether they were or to match the pre-intervention women with the post-intervention women. And so you can see that there's a number of a lot of variables here that would be typical to maternal fetal medicine. So what we are going to do is we're going to match at 0.0001 or less. So we have almost 3,500 pairs, or 68% of our total population that we have available. But it turns out that about 3,200 or so had to be discarded because we were not able to match. So we ended up with a little over 1,400 intervention pairs, which is about 41% of the total population that we had to work with. So here's just the output to show how this works. And so on the left-hand side, we have the year after the intervention, 2006, and individual patients and the birth weight of their infant. And then on the right-hand side, we have those pre-intervention in 2004. So the far right column gives us the propensity score difference. And so you can see that there's several that are almost matched perfectly, where the difference is essentially zero. And then you can see that the difference gets larger. I've got them sorted by the size of the difference here. But remember that we need to match those who were participated in the intervention in 2005. So we have, even though we have a match here, there's some who did not participate in the intervention that we have to exclude. And so we would go through our data, and then this is how we would identify those who participated in the intervention and their propensity score. So we would have, so for example, the first three would be really good matches, since the difference is virtually zero. And then the very last line there, where the propensity score is still less than our cutoff of 0.0001. So in this case, we have pre-post match pairs. The intervention, no intervention is our outcome, or is our variable that we want to determine if it makes a difference in birth. In this case, birth weight is the outcome. And so this is our, what we call our between subjects factor. And then pre and post, the within subjects factor is now correlated, and they're correlated not because they're the exact same patients, but because they matched with respect to their propensity scores. So what we're doing is simulating a randomized trial where the confounding factors are balanced out via the propensity score. Obviously, this is not perfect, but it is one way of trying to eliminate selection bias in a non-randomized study. So we have correlated data, and regardless of whether it's continuous or binary, we're going to do some sort of paired test. In this case, it's going to be a paired t-test, or we can do a general linear model where we have repeated measures at the 2 time frames, year 2000 and year 2006. And as I mentioned, it's paired because it's correlated, or the data are correlated because we've matched with the propensity score, even though they're, individually different patients. And so this is our result, just doing a paired t-test. So we can see that there is a statistically significant difference of 61 grams, I guess it would be, 3434 for the pre-intervention and 3495 after the intervention. So in this case, we would, because we can reject the null hypothesis, we would conclude that our intervention had an impact. So just to give you an idea here, this is how the data would be set up. We call this long data in contrast to wide data. So we have the intervention patients here matched from year 4 pre-intervention, year 6 post-intervention. And so the ID links the 2 that are matched by propensity score. And so if we did the general linear model, where we look at, in this case, we'll look at year as the intervention. And so here, what we would get is the intervention difference that we saw in the paired t-test of 61 in the constant here. This would be the average birth weight for those at 4 years. Okay, so that's an example of doing matched pairs or matching by a propensity score. So I want to look at a study that we did a while back on looking at the use of inverse weighted propensity scores. And so in this analysis, we linked 2 different registries, the National Cardiovascular Data Registry and the STS Adult Cardiac Surgery Database to claims data from the Centers for Medicare and Medicaid Services for the years 2004 through 2008. And so outcomes, in this case, survival, were compared with the use of propensity scores and inverse probability weighting. So actually we did both propensity score matching and inverse probability weighting, which is often done. And so, of course, what you would like is that they both agree as far as your results are concerned. If they don't, then you have some sort of issue. But anyway, what I'm going to show here is the inverse probability weighting. So we have a really large number in the PCI database, 1.5 million, and over 500,000 for the STS database that looks at coronary artery bypass. And so we end up with a little over 100,000 patients who underwent PCI and some 86,000 patients who underwent CABG. And those are the patients that are included in the analysis. So this is just taken from our article, but I wanted to just highlight the fact that we're studying coronary or cardiovascular patients who underwent percutaneous coronary intervention versus those who underwent CABG or coronary artery bypass. So obviously, these patient populations are going to probably differ substantially with respect to pre-procedural characteristics and as well as possibly demographic. We use then propensity scores to adjust for these between group differences as far as the baseline characteristics from patients and from hospitals. And so this is a graph of the propensity scores, in this case for CABG. So this is what you hope to see when you calculate the propensity scores. If there's a certain amount of overlap, a really good amount of overlap between the two. And actually it has to have this overlap in order for the inverse probability weighting to work. If you get distributions that look like this, then you have a problem. In fact, you wouldn't be able to do any kind of analysis because basically your propensity scores identifies the treatment groups, as there's virtually no overlap in the propensity score distributions. And so here is our table 1, where we have the unadjusted data, and you can see on a number of demographic and clinical variables, they virtually differ on every single one of them, except for a couple. After we used inverse probability weighting to adjust for these differences, then you can see that they're quite close, and that there's, except for one, no statistically significant difference between the two groups. So in other words, what we've created here is a pseudo-randomized study where the intervention groups are more or less equally distributed with respect to potential confounding variables. And so this is the graph of the outcome, is just survival, and there's actually very little difference between the two, is in the graph that you present from 0 probability to perfect probability of 1. The inset is usually put in there to show finer details when you don't have much of a difference in this case in survival between the two. And so you can see that what happens here is that there's an initial benefit for PCI, but over time, the benefit is on the side of a coronary artery bypass. In other words, they have a better survival than the PCI patients. And again, the difference isn't real great, but of course, with the number of patients that we have, they're going to be statistically significant. And so that you can see that the relative risk in the bottom line there, 1.72 at 30-day mortality favors a PCI, but you can see that this decreases over time, and at 1 year, it actually begins to favor the cabbage patients. And so what we did, or the other statistician actually did, was to do a sensitivity analysis where we looked at the effect of unmeasured confounding factors. And so on the plot here, the vertical axis is hazard ratios for death associated with the confounder. And then the horizontal axis is the prevalence of the confounder in the PCI group. And then we have different percentages of the presence of the confounder in the cabbage group. And so, for example, what you see that if a confounder was present in 10% of the patients in the cabbage group, that would be the dark green line in the graph. But only in 35% of the patients in the PCI group, which would be right here, you can see then that the increased risk of death is more than twice that. So that would mean that if that confounder is present in those proportions in the two groups, then that could account for the difference in mortality between the two groups, and we would not be able to conclude that one group is better than the other with respect to mortality. So I don't know that this is actually done a lot in propensity score analysis, but it actually should be, because that is the one thing about using propensity scores is because they're based on variables that you have available. If there's a variable that you haven't measured, then it's a potential confounder that could really alter your results. So I'll summarize here. The propensity score is the probability of assignment to a group, a treatment group. If the probability of being in group A is P, then the probability of assignment to group B is 1 minus that. And we get this probability from logistic regression, which I've given you an example there where the X's are the covariates, or the variables that we think might influence the probability of being in one group or the other. And so, as I mentioned, we get a pseudo-randomized sample. And the probability then we get from the logistic regression equation, where the probability is just the exponent of the regression equation divided by the exponent of 1 plus the regression equation. And so that's, we get our probability from that, which is then our propensity score. And then if we're using inverse weighting, we use the inverse of that in the comparison of the two groups. So, and then as far as matching goes, we match patients in each group by the closest propensity score. And so you'll need to specify the precision you want. Do you want to match within, say, 10 to the minus 2 or 10 to the minus 3, 10 to the minus 4? You probably want to do more than minus 10 to the minus 2, but anyway, that's a decision that has to be made by the investigator. And then remember that in doing a matching, that about a third of the sample won't match, and so you will have and about a third of the patients will be excluded from the analysis. So inverse probability weighting, as I mentioned, we specify as weights in the regression analysis and usually the software like SAS, Data, R would do that. You specify what the propensity score is and use that as a weight in the comparison between the two groups. And the advantage of inverse probability weighting is that you can use all patients in the sample. So I have some references here. The first one being our study on revascularization strategies of using inverse probability weighting. And then I've got a couple there where, of course, as you might guess, there's limitations or there's arguments for not using propensity scores. In the last one, should not be used for matching. That, of course, is debatable, and it would have those that would argue that that's probably too strong a statement to not be used. So I want to then we have a little some time for questions and answer. Let me see if I can. I think we have at least one here. Okay, is there a minimum number of patients needed to calculate significance using these methods? Well, I think that that's true of even randomized trials. So if you do like a power analysis to calculate the number of patients you're going to need, you would need to do that before you use any propensity score method is how many you would need to show statistical significance. Now, I will say that when you have paired data, that's more powerful. You have more power using paired data than you do using unpaired data. But the minimum number of patients you would need would be dependent on the effect size that you want to see. Okay, is there, let's see, any other questions? Okay, if not, we can end the session early. I will say that the presentation here has been recorded, and the folks at Georgetown will send that out, or the link to the recording, and I send them the slides, and they will send people who have registered this for, we'll send registered for the seminar, we'll send the slides to you. So the lowest precision of match, well, I would say probably 10 to the minus 4. In other words, like 4 decimal places, like 0.0001 would be kind of the minimum that I would suggest using. Probably a better one, would be 10 to the minus 6 or even 10 to the minus 8. What some individuals or some programs do, in fact, I think there's a SAS program that does this, that's their greedy matching, is you start out at the lowest precision that's possible, and then you match until you're up to whatever the sort of the upper limit you want to go to, or you want to match on. But I would suggest matching at least to 10 to the minus 4th, and even better than that, 10 to the minus 6 or 10 to the minus 8. Okay. Yes, you can have only one outcome variable in the analysis that we did here. If you have more than one outcome variable, then you're going to do multivariable analysis. And that's a little harder to do. I've just used the one outcome variable here because that's, you know, easier to see, but it would be possible to have more than one outcome variable, and you would be doing multivariable analysis then. But the multivariable analysis become a little tricky to interpret because you have a linear combination of your outcome variables. So, but you could still do, you know, matching, because that's, you know, you do that with the covariates that you can match on. So you could do the matching or the inverse probability weighting. Okay, let's see here. Okay. Any other questions? Okay, if you do think of some questions later on, you can send those to me at my email address, my MedStar, paul.kolm@medstar.net, and I'll be happy to respond to those. So I want to thank you for your time and attention, and we will have one more of these this year in December. I think it's right before the Christmas weeks, but we'll then, after that, we'll start again in the new year.